In 2025, 780,000 tons of electric vehicle batteries reached the end of their automotive life worldwide. Following the traditional playbook, these batteries would be shipped off to recycling facilities where they'd be dismantled, smelted, and refined into raw materials for new batteries. But here's the overlooked truth. 50 to 80% of these retired batteries still have perfectly good storage capacity left in them. Meanwhile, halfway across the globe, AI data centers are facing a full-blown power crisis. By 2030, global data center electricity demand is projected to hit 945 terawatt-hours, equivalent to Japan's entire annual power consumption. Building new power plants takes years, new lithium battery storage costs a fortune, and AI companies can't afford to wait. On one side, you've got semi-functional batteries being treated as trash. On the other, you've got data centers desperately hungry for power. When these two seemingly unrelated industries collide, a $100 billion market is born. In June 2025, the company Redwood Materials took 792 used electric vehicle batteries and built a 63 megawatt-hour microgrid in just 5 months to power AI data centers. The cost? Half of what a new battery solution would run, with construction time slashed from 2 years down to 5 months. This isn't some feel-good environmental story. It's a high-stakes business game about asset revaluation, supply-demand matching, and the fight to control industry standards. The answer to how billions of dollars in assets transform from waste into gold lies right here in this industrial revolution. To understand this market opportunity, you first need to wrap your head around one question. Why do batteries with 50 to 80% capacity still have to be pulled from vehicles? Behind this lies a brutal economic logic. When an electric vehicle's battery capacity degrades to 80%, it means a 20% reduction in driving range. A car that could once go 500 kilometers now only manages 400. For owners, this isn't just about heightened range anxiety, it's the beginning of asset depreciation. The used car's value takes a nosedive because buyers worry about how much longer the battery will last. This is the commercial tipping point for battery retirement. It's not because the battery is completely shot. It's because its value in that specific use case drops below the cost of continuing to use it. Car manufacturers typically recommend replacement when battery capacity falls to 75 to 80%. This threshold is set based on a combination of user experience, safety margins, and brand reputation considerations. For years, these retired batteries had only one destination: recycling. The entire process involves tearing batteries apart, extracting lithium, cobalt, nickel, copper, and other precious metals through high-temperature smelting and chemical leaching, then selling these materials back to battery manufacturers. Sounds eco-friendly, but the economics don't really add up. Recycling 1 ton of retired batteries costs roughly 8,000 to 12,000 yuan, covering logistics, disassembly labor, smelting equipment depreciation, and environmental treatment fees. The value of extracted materials, however, heavily depends on raw material market prices. In 2022, when lithium carbonate prices shot up to 600,000 yuan per ton, recycling companies were printing money. But by 2024, lithium prices had crashed to around 100,000 yuan per ton, and many recyclers were bleeding red ink. The real contradiction runs deeper. Recycling processes only care about material value while completely ignoring storage value. A battery at 80% capacity could theoretically deliver another 3 to 5 years of stable power output if kept in service. Using energy storage market pricing standards, each kilowatt-hour of storage capacity is worth about 800 to 1,200 yuan. A 60 kilowatt-hour battery pack with 50% capacity remaining, that's 30 kilowatt-hours, has a storage value of 24,000 to 36,000 yuan. Meanwhile, the materials extracted after dismantling are often worth less than 10,000 yuan. From an asset depreciation perspective, this is massive waste. The core value of a battery as an energy storage asset is its ability to store and release electricity, not just which metal elements it contains. When we immediately tear apart a battery that could work for another 3 to 5 years, it's like demolishing a house that could be lived in for another decade just to sell the steel and concrete. On paper, it fits the logic of resource recycling, but in reality, it destroys enormous utility value. In 2025, if the 780,000 tons of retired batteries globally are calculated at an average of 50 kilowatt-hours per vehicle with 50% remaining capacity, they could theoretically provide about 200 gigawatt-hours of storage capability. At 1,000 yuan per kilowatt-hour, that's 200 billion yuan in dormant assets. But if it's so valuable, why hasn't anyone made this business work for the past decade? That brings us to the concept of cascading utilization. The concept of cascading utilization has been floating around the battery industry for at least 10 years. The logic is simple. Batteries retired from cars get used in lower performance scenarios, squeezing out every last drop of value. But reality check. By 2024, the global cascading utilization market was still less than 10% of the overall battery recycling market. A seemingly reasonable business just couldn't get off the ground. The root cause? 3 insurmountable barriers. The first barrier is technical. The standardization nightmare. There are dozens of major electric vehicle brands globally, and each one designs its battery packs differently. Tesla uses cylindrical batteries, BYD uses blade batteries, and CATL, that's Contemporary Amperex Technology Co. Limited, has both prismatic and pouch batteries. Size, voltage, interfaces, communication protocols, none of it standardized. If you want to integrate old batteries from different brands into one system, you have to develop custom adaptation solutions for each one. That means sky-high R&D costs and complex supply chain management. Even trickier is battery consistency. Even batteries from the same brand and batch, after years with different owners, degrade at wildly different rates. Some people fast charge daily and drive aggressively. Their batteries degrade fast. Others gentle charge and baby their cars, keeping batteries in great shape. When you cartelane a battery with 80% capacity remaining with one at 50%, the weaker one becomes the bottleneck for the entire system, dragging down overall performance and potentially creating safety hazards. The second barrier is economic, cost inversion. In theory, used batteries are cheap, so cascading utilization should have a cost advantage. But in actual operations, you need to test each battery's health status, requiring specialized equipment and technicians, dismantle and reassemble battery packs, high labor costs, develop or purchase battery management systems, software and hardware investment, assume safety and warranty responsibilities, insurance and after-sales costs. Run through this entire process, and the total cost often isn't much lower than directly purchasing standardized new batteries. A 2023 industry report showed that the cost per kilowatt-hour for cascading utilization batteries was about 0.4 to 0.6 yuan, while new lithium iron phosphate batteries, thanks to economies of scale and technological progress, had dropped to 0.5 to 0.7 yuan per kilowatt-hour. The price gap is too narrow to compensate for cascading utilization's disadvantages in performance stability, after-sales service, and brand trust. The third barrier is market-based. Application scenarios are too narrow. Cascading utilization's originally envisioned scenarios were low-speed electric vehicles, electric two-wheelers, and backup power for telecom base stations. But these markets are limited in scale and extremely price-sensitive. Low-speed vehicle companies would rather use the cheapest lead-acid batteries than risk using old lithium batteries of questionable origin. Telecom base stations require extreme reliability, and operators won't gamble with backup power. This created a vicious cycle. Because application scenarios are small, economies of scale can't form, preventing unit costs from dropping. Without lower costs, no customers want to use the products. Without customers, companies can't validate business models, and investors won't put money in. Plenty of companies in the industry have tried cascading utilization projects, but most remain small-scale pilots that couldn't turn a profit and eventually fizzled out. Automakers' attitudes are even more complicated. In theory, automakers recycling their own branded batteries for cascading utilization should have natural advantages. They know their battery designs and performance inside and out. But in practice, automakers would rather sell new batteries. A new power battery can achieve 25 to 30% gross margins, while cascading utilization batteries, even if they could scale, would only deliver 10 to 15% margins. What's more, if large quantities of used batteries flood the market, it could impact new battery sales. From a business logic standpoint, automakers lack sufficient motivation to push this self-competing business. By the end of 2024, cascading utilization looked more like a textbook case of being politically correct but commercially failed. China issued the interim measures for the management of recovery and utilization of power batteries for new energy vehicles. The EU rolled out the new battery law, and governments worldwide were encouraging the practice, but the market just wouldn't take off. And just when everyone was about to give up, an unexpected buyer appeared. At the end of 2024, when the AI data center operator Crusoe approached Redwood Materials, they made what sounded like a crazy request. Could Redwood build a microgrid system capable of 24-hour power supply within 6 months? The location was in the Nevada desert, with no grid connection, relying entirely on renewable energy and storage. Behind this demand lay the power predicament facing the AI industry. Training a GPT-4 level large language model consumes about 10 to 20 megawatt-hours of electricity, equivalent to an average American household's 200 years of power consumption. As OpenAI, Google, Meta, and others race to scale up computing power, data center electricity consumption is growing at an alarming rate. U.S. Department of Energy data shows that in 2023, data centers consumed 4.4% of America's total electricity. By 2028, that proportion will surge to 6.7 to 12%. Grid expansion can't keep pace with AI expansion. The traditional solution is apply to power companies for capacity increases, wait in line for grid upgrades, a process that typically takes 2 to 4 years. But for AI companies, time equals competitive advantage. Every day of delay means market share getting eaten by competitors. Some tech giants have even started building their own small natural gas power plants, but this contradicts their publicly promised carbon neutrality goals, exposing them to massive public pressure. What caught Crusoe's eye were precisely those retired electric vehicle batteries in Redwood's hands. This was perfect supply-demand matching. From a technical requirements perspective, data center storage scenarios are completely different from electric vehicles. Cars need batteries that are lightweight, energy-dense, and can handle rapid acceleration and braking. Fixed storage systems don't care about weight, require lower energy density, and involve relatively smooth charging and discharging. Batteries that are performance insufficient for cars work perfectly fine in storage scenarios. A battery with 60% capacity remaining can only go 300 kilometers in a car, but in a storage system, it can still charge and discharge stably for 3 to 5 years. From an economic model perspective, the cost advantage is strikingly obvious. Building a 63 megawatt-hour storage system with brand new lithium batteries would cost about 300 million yuan in equipment alone, plus land, installation, and commissioning, bringing total investment close to 400 million. But Redwood's used battery solution can slash equipment costs in half to 150 million yuan. While it increases some operational maintenance costs, you need to periodically replace battery packs that degrade too quickly. The overall ROI, return on investment, still significantly beats new battery solutions. From a time value perspective, this is the killer competitive advantage. Redwood's solution doesn't require redesigning battery packs, doesn't need long-cycle customized production, doesn't require complex environmental impact assessments because the batteries already exist, they're just being used in a different scenario. In June 2025, from project launch to grid connection and power generation, Redwood took just 5 months. For AI companies desperate to expand computing power, that speed is worth its weight in gold. The technical breakthrough was Redwood's Universal Translator System. This is an intelligent battery management platform, whose core function is enabling batteries of different brands and degradation levels to peacefully coexist. The system monitors each battery's voltage, current, temperature, and health status in real time, dynamically adjusting charging and discharging strategies. When a battery's performance drops below the threshold, the system automatically flags it. Workers swap in a new battery pack with a forklift. The entire process takes less than 30 seconds with no downtime required. The essence of this business model is transforming selling products into selling services. Redwood doesn't simply sell old batteries to data centers. It provides a complete energy storage as a service solution. We provide the battery arrays, management systems, and operational maintenance services. You just pay per kilowatt-hour usage fees. This model lowers customers' initial investment barriers while allowing Redwood to continuously earn service revenue. When batteries are completely spent, they can recover and extract materials, achieving a complete utilization to recycling closed loop. In July 2025, just 1 month after Redwood's project went live, General Motors announced a strategic partnership, providing both new and used American-manufactured batteries for storage projects. Almost simultaneously, the data center divisions of Microsoft and Google began reaching out to Redwood, inquiring about similar solution feasibility. A cascading utilization market stuck in neutral for 10 years suddenly found its breakthrough moment thanks to AI's power hunger. When application scenarios are large enough, customer willingness to pay is strong enough, and time value is high enough, previously insurmountable technical and economic barriers become crossable. Redwood's successful validation triggered a chain reaction worldwide. This isn't just a business opportunity, it's a race for industrial standards, technical pathways, and market dominance. China and the United States are taking completely different approaches in competing for control of this $100 billion market. The American model's core is technological platformization. Redwood's role is more like the Uber of energy storage. It doesn't produce new batteries, doesn't operate data centers, but builds a technology platform integrating upstream retired battery supply with downstream storage demand. This asset-light model's advantage is flexibility and rapid iteration capability. Redwood has already struck battery recycling agreements with over a dozen automakers including Tesla, Ford, BMW, and Toyota, ensuring stable raw material supply. Simultaneously, through its universal translator system, it standardizes the compatibility issues of different branded batteries, reducing the marginal cost of scaling up. But the American model has obvious shortcomings. Strong supply chain dependency. US domestic electric vehicle penetration is far below China's. In 2025, the US sits at about 15% compared to China's over 50%. This means limited retired battery supply. American battery manufacturing capacity also depends on imports, creating massive uncertainty amid escalating geopolitical risks. While Redwood secured a $2 billion low-interest loan from the US Department of Energy, establishing a complete domestic battery circular economy industrial chain still takes time. The Chinese model is vertically integrated closed-loop. Battery giants like KLA and BYD control the entire industrial chain from battery R&D, manufacturing production, vehicle installation, to recycling and cascading utilization. This model's advantage lies in economies of scale and cost control. In 2025, China's energy storage battery shipments are projected to reach 324 gigawatt-hours, with KL alone capturing 36.5% of the global market. More critically, Chinese companies can accumulate massive data directly from their self-produced batteries to optimize battery management algorithms, something American companies struggle to match. The numbers are even more striking. In 2025, China's power battery retirement volume hit 780,000 tons, calculating at an average of 50 kilowatt-hours per vehicle with 50% remaining capacity. That provides about 200 gigawatt-hours of storage capability. During the same period, China's new energy storage installation demand exceeds 130 gigawatts. If calculated at 4-hour storage duration, that requires 520 gigawatt-hours of battery capacity. Theoretically, China's retired batteries alone could satisfy about 38% of new storage demand. This is a massive pie with annual market size exceeding 200 billion yuan. But the Chinese model's hidden worry is innovation flexibility. Because automakers and battery factories do both new batteries and cascading utilization, internal left-hand, right-hand conflicts exist. Will promoting cascading utilization batteries impact new battery sales? This concern to some extent limits companies' push efforts. Additionally, China's cascading utilization is mainly dominated by battery factories and automakers, with relatively limited space for third-party independent operators, potentially affecting business model diversification exploration. From an investment perspective, this industrial chain has 3 key value points. First is the technical barrier segment. Battery management systems, BMS, intelligent operations platforms, thermal management technologies, and other core technologies are the moat of the entire business model. Companies mastering these technologies can achieve higher profit margins and pricing power. Redwood's Universal Translator System and KTL's CTP, cell-to-pack technology all fall into this category. Second is the economies of scale segment. Whether American or Chinese model, ultimately it's about using scale to reduce costs. Companies first achieving 100 megawatt level and gigawatt level deployment will dominate cost competition. That's why Redwood, immediately after its first pilot project succeeded, announced it was designing a project 10 times larger. The time window is fleeting. Third is standard-setting power. The EU's new battery law requires all batteries to carry battery passports recording full life cycle carbon footprints, material sources, health status, and other information. China is also advancing power battery traceability management platform construction. Whoever can lead these standards formulation will dominate future global trade. This isn't just technical competition, it's rules competition. Risk factors equally demand attention. On the supply chain end, if battery technology breaks through, say solid-state batteries achieve mass commercialization, extending battery lifespan from 8 years to 15 years, retired battery supply speed would dramatically slow. On the demand end, if the AI bubble bursts or data center construction slows, storage demand growth would decline. On the safety end, used batteries' thermal runaway risks always exist. One major accident could trigger tighter regulations, impacting the entire industry. But even considering these risks, this market's fundamentals remain solid. The International Energy Agency predicts that by 2030 global energy storage installation demand will exceed 600 gigawatts, corresponding to over 2,000 gigawatt-hours of battery demand. Meanwhile, globally retired power batteries annually conservatively have hundreds of gigawatt-hours of usable capacity. As long as technical compatibility, cost control, and safety management, these three major problems can be solved. This is a trillion-level industrial opportunity. From 780,000 tons of retired batteries to a $100 billion storage market, this story reveals a long-overlooked business truth. The greatest value in circular economy doesn't lie in turning waste into raw materials, but in redefining the usage boundaries of assets. A battery that retires from automotive service can continue delivering value in a different setting. The key isn't how advanced the technology is, but whether you can find customers willing to pay for that remaining value, and whether you can build a business model that keeps this exchange running. AI data centers' power hunger unexpectedly provided the answer to a problem that's plagued the industry for 10 years. As China and the US compete for market dominance through different pathways, the real deciding factor isn't whose battery technology is stronger, but who can first establish a complete industrial closed loop of retirement testing, matching, application, recycling, and export that loop's standards globally. The finish line of this race might redefine our understanding of concepts like assets, waste, and circulation. In a future where new energy and AI intertwine, the logic of value creation is being completely rewritten,